Okay, first of all, let me thank you for organizing this great workshop, for allowing me to talk about this joint work with Thomas Mertens and Gabriel Wong. So, in a nutshell, just to try to here I have a bunch of questions which in some tangential way I'm going to try to share some of our ideas and I should say some of our conclusions. So one of the questions that is motivating our work in some really effective setup is to understand this famous question of understanding what is the bulk microscopic interpretation of the area term. I should stress the word bulk here. And in particular, to re-stress that, one of the questions that I'm going to be asking, which has been asked before, of course, is whether this black hole entropy allows any kind of gravitational entanglement entropy interpretation. Some expectations in the literature based on work by Saska and Urum and people actually outside of our community may suggest that gravity, in fact, regularizes the notion of entanglement entropy. I'm talking back to the observation that when you do entanglement calculations, as all of you know, in a continuum quantum field theory, you get infinite axons. Another question that motivates me to ask this question in the specific context of a black hole, but hopefully one understands that case, then the anti-formula would have a similar interpretation, is what glues space-time together. Surely these days, especially in our community, we would say that the answer is entanglement. But in order to define entanglement, as it has appeared in our talks already in this workshop, you first of all, from a bulk perspective, you need to have a factorized Hilbert space. And as Subrat and others here have stressed, that's not the case. Also, in a gravitational invariant theory. However, these questions in gauge theories, I'm not saying that gauge theories have the same problems as in gravity, but this problem of factorization also arises in gauge theory. So here I have a picture in which I'm just heuristically choosing some entanglement surface that is splitting Wilson loop. And then in that case, it's not only that there is any factorization. Now, some of the techniques to deal with that with this situation in the gauge theory case involve some introduction of some factorization map. Sorry, the notation is a little bit confusing with regard to the notation. So there is, in principle, there is no error correction here, though everything is related, as you know. So here right now in particular I'm talking about gauge theory in a fixed background. So I'm just mapping the actual physical Hilbert space into some explicit factorized Hilbert spaces in the sub-regions B and B bar by introducing some splitting region epsilon. And then the picture that emerges in those setups is that these Hilbert spaces involve some what they call entanglement edge modes, which are charged under some group, which in the gauge theory discussion is typically large gauge transformations. And the way to recover the physical Hilbert space in that case is by projecting the structure that you find in this larger extended Hilbert space to the subspace of basically singlets in this setting. Now, once you have that structure, you have a well-defined notion of tracing, you have some well-defined notion of factorization, and then using the von Neumann entropy, if you are technically strong enough, you get some answers. And in particular, you get some divergent peaks, let me call it as bulk for the sake of this slide. And then there's some explicit contribution, which is associated with this with this entangling modes that you have discovered appearing in this splitting region.
Sorry, is there a canonical choice of the extended Hilbert space?
As far as I understand, the answer is no. So we can also ask, you could define different factorization maps and you could get, exactly. So the answer is no. And one of the questions that I'm going to ask is which constraints we may want to put as a theoretician, let's say, in order to try to come up with a canonical answer. Okay. That's only my understanding. Sure, yeah, of course.
The way this H-series factorization works is, of course, we add a degree of freedom where we can add appropriate negative or positive charges to soak up.
Yeah.
But that doesn't work that's the first difference in gravity, right? Because you don't have negative gravitational charges. So the same technique of just putting something which allows, you see what I'm saying? Usually, H-series, the way you factorize the Hilbert spaces, you add some boundary degrees of freedom, and those just satisfy the Gauss law, because they just have the appropriate charges possible. But in gravity, we can't do that. So it's not great. So isn't that a very important difference by the analogy?
Well, what I'm going to try to do is I'll go to 3D and then I'll use the Joan Simón formulation in 3D, and I'm going to try to borrow these tools. But I'm highlighting a little bit of so I'll try to impose a condition which ensures that the partition function that you compute in the full gravitational theory, let's say, when you remove the cutoff that already Hawking and Gibbons put, the analogous partition function in that limit recovers this partition function. That's the most important technical aspect of the talk. And what we will learn is that there is some non-trivial density of states which in the extremal limit would recover the singe that was appearing in. So I don't have a good understanding of this splitting in terms of A and M bar that you were alluding to. But when I describe the theory in terms of non-local degrees of freedom Wilson loops, which is a luxury, I admit, that I may only have in 3D, but I'm trying to get some mileage about, a generic question that we could ask. I didn't want to mention it, but this perhaps in the more general higher dimensional formulation that Wood and Pennington and company have come up with the one-Neumann algebras. Just by including these zero modes that guarantee that the mass of the two boundaries are the same. It allows them to discover this regularization effect in the sense that without adding that specific pair of conjugate momenta, which is purely gravitational, before doing that you don't have a trace. When you include it, you have a trace. Here, without playing that game, in principle, I'm doing it more non-perturbatively. If you allow me to use our language, you will see why I feel a little bit. But I don't, we have more confusions than answers. But I'm happy to come back. Yeah. In particular, the representation theory of the AA bar that you are alluding to, I don't have a sharp physical answer.
Just one more question about setting. In ADCF, usually when we do this, we almost always look at a region which extends out to infinity. So if you look at a standard entanglement,
yes.
In that case, I think it might be the case that there is a good factorization also in the past. Is that the kind of region you will be looking at, or will you be looking at a compact region?
I will be looking at in this talk to the case of a two-sided black hole, and I will keep the entire exterior from an asymptotical observer.
So then
yeah. But for reasons that I hope that will become a little bit more apparent in a few minutes, I'm hoping that some of these ideas may apply to an RT surface analysis.
Sure, but that's also fine.
But that's also fine, yeah. You are alluding to the argument that you realized the other day about having a compact region.
Yeah, I'm only worried about compact.
Right. So in that case, to be honest, I have not thought about it. But it could be worth to see what would go wrong in this kind of language. Okay. So answering that question has provided that, but I will still convey, of course, So to recapitulate, there are these methods which I have not defined for you, but I'm telling you a little bit what is the outcome of that very nice story. And manual questions that you may ask independently of the more broader pictures the broader question that I already asked is, can I use these methods in gravity? I think it's important to stress whether there will be just analogies, and if there are differences, what are the differences? And I'll try to, if I don't convey other things, I'll definitely try to convey something that I thought I learned out of this investigation. And in particular, just to motivate technically what we are going to do, I'm going back to this issue of what glues space-time together. This is a question that you could ask in JT or in 3D gravity, even without including matter. So, even if you don't have gravitational wave perturbations, you still have solutions of GR gravity. The space-time is glued together. So if these gravitational entanglement modes do have a role to play, they should be there independently of whether there are gravitons or not around. So that's another, it sounds silly, but it's another reason to play with history model that also appears in Argent's talk and in many people's work. Okay, just in case of providing some picture, though the discussion that we will be having is going to be a little bit misleading, but I'm hoping that this will help for people that have not thought on these kind of problems. One person that in recent years I thought that expressed some of these difficulties in a very explicit way, so I'm borrowing his pictures. So I'm going to rephrase some arguments by Harold some years ago. He considered a two-sided black hole in ABS. In the context of ABS, you have an explicit bulk factorization in terms of the Hilbert space in the left and in the right. That's what I'm trying to allude here. But if you consider gauge fields in the bulk, I should have stressed this word, bulk. When you take that slice, that bushy slice, the dotted line, this is the bridge. And when you include this, you could consider some Wilson line that goes from one boundary to the other. This is a non-local degree of freedom, which is gauge invariant. So from that perspective, it makes very, very manifest that even though in that picture you have an explicit factorization from the boundary perspective, the bulk effective description of this Wilson line makes it highly non-trivial, like in the gauge theory discussion that we were having more in abstract terms. But in terms of pictures, if you use the extended Hilbert space picture, what you are trying to go after is a splitting of your Hilbert space into something that you may call HB bar, which is the left asymptotic Hilbert space. The HB would be the Hilbert space of the right observer, if you allow me to use this graph. And then at the entangling surface, you are literally cutting your Wilson line in terms of, but you need to tell me how this thing ends in a gauge invariant way. So since this Wilson line transforms under the gauge group, this A and A bar, which is what Subret was alluding to, they have to transform under that group. Okay? Now, the edge, the contribution of these modes to the entanglement entropy is typically the logarithm of the dimension of the representation, where the guys are transforming. Now, this is where I'm going to switch gears, so the picture is going to be slightly different, but think about this splitting of the Wilson line, if you want to. You may have seen this picture many times. I'm not necessarily advocating that I believe in this or not. At this point, it's just a picture. The classical representation of the two-sided black hole in ABS has this Pembroke diagram representation. And what we would like to do is find a factorization of the space-time itself. That's the only thing that the picture is really trying to do. In the previous picture, if you want to, notice that the wormhole has not been cut, and the only thing that I'm cutting is the gauge degree of freedom. What I'm trying to stress, even though it may sound silly, is that I am after the cutting of the ER bridge itself. That's why I'm insisting that this is bulk gravity. Okay. So I hope that this goes through. Many people have, of course, thought, suggested, made progress, asked the question about the relevance of these H modes A and A bar in quantum gravity. And coming back to one question, in order to start trying perhaps a slightly more precise questions, we would ask which factorization, if I want to borrow these ideas, which subset of factorization maps are going to be useful, because indeed there is no canonical construction, is there any relevant constraint, and which groups and what is the spectrum of representations where these guys are going to transform. And this is what I will try to give precise answers in this talk. Maybe more philosophical remarks, but in the context of 3D gravity with a negative cosmological constant, we'll try to give an answer for GS, the spectrum of representations, and we will pick some specific factorization maps. You may try to come up with the, other ones, but that I'm just alerting you that that's what we are aiming here. So for those of you that are more technically oriented, for good reasons of course, let me remind you that in lower dimensional gravity, the reason, if you want to see more explicitly, technically, where the lack of factorization emerges, for instance, in JT gravity, Harlow and Jeffreys just quantize JT gravity, the Lagrangian that Arjun wrote down, but without the grain sources. And in that case, you have the symplectic form in the Hamiltonian formalism can be written as literally as a manifest pair of a quantum mechanical system, where P is roughly related to the energy of the Hamiltonian, but more importantly, there is some regularized geometry that depends on some regularized distance between the two boundaries. And this is what makes manifest that you cannot measure these things if you are an observer in a single site. So this is one way of phrasing the lack of factorization.
Just one question. This is in the absence of any matter in the
Yeah, absolutely, yes. And whatever I'm going to do today is in the absence of matter.
Also, there's something I've never understood. Is it understood how this quantization relates to the Schwarzian? I mean, this gives you only 2 degrees of freedom, right? One length and one conjugate diameter.
Right.
And then there's all this technology developed using the Euclidean path integral and the Schwarzian. Is it understood how this answer is related to that answer? Standard Schwarzian description?
It is. You take 2 Schwarzians on the 2 boundaries of ADS, but they have to be glued together. So that naively, that has a higher dimensional phase space than 2, but you have to impose the gauge constraints. And setting the SL2 charges to 0 will give you back a 2-dimensional phase space, which is this one.
This is understood in surface space.
Yeah.
In a sense, this is the lower dimensional, what you have just described is the lower dimensional description of what happens in 3D. So in 3D, if you do the quantization of 3D gravity around some eternal BTC black hole, like Goldberg and Jensen, but if you prefer NOAA, different people have slightly different technologies, but they are solving the same problem. You have some non-trivial Wilson line representing the black hole in the radial direction. And you have the boundary stress tensor, if you allow me to use as the degrees of freedom. So you would think that you have 2 copies of the Asoro excitations in both boundaries. This looks like a factorized Hilbert space. But the issue is the existence of, you need this gluing condition ensures that the mass and the angular momentum of the black hole measured by both boundary Hilbert space is the same. This is actually the mode. I'm simplifying things a little bit, but physically, this is actually the mode that Witt and Pennington and company are talking about. This is the mode that exists in any higher dimensional theory. And this is what I was trying to stress here, because this is known in some literature.
What did you just say, Pennington, Whitman?
Sorry, there are other authors, so I apologize for that. But I'm referring to the paper in which they are...
Algebraic group theory.
Yeah, the von Neumann algebra story. Yeah. So in that story, in order to... Yeah, okay, sorry. Yeah, this is not my work, so I should not highlight it. But I definitely want to highlight that the common thing here concerning the lack of factorization, which was your question, is the existence of this constraint. And that's precisely what those authors are building on. Yeah, sorry, I've said this. Okay, so coming back to Onkel's question, some people before us, Donnelly, Wong, and Jeffrey and Hofmeier also thought about this in the context of the lower dimensional gravity. They also asked the question, okay, I would like to factorize gravity in this two-boundary setup for eternal black holes. What kind of factorization can I do? And one thing that you may want to do, this could be discussed from minute zero, but one idea that you may have is, okay, perhaps I want to be guided by locality as a constraint on this factorization map. And here, it's useful that Arjun already went over this. Here, I'm reminding you of the Euclidean construction of the thermofield bubble. Once I have included this regularization cutoff surface. And in the left-hand side, I'm reminding you of the Hartle-Hawking discussion that he was having when answering Oliver's question. So I have a disk, but now I view it as the norm of the Hartle-Hawking. But once you introduce this regularization surface, in the limit, when this size of this small hole is finite, what you have is an analogous. And the condition that I'm going to impose is what these authors call the reasonable boundary condition, which is I'm interested in studying this partition function in the existence of this hole, if you allow me this. But when I take epsilon going to 0, I would like to reproduce the exact, if you have an exact answer for the partition function of the disk. Now, one thing that I would like to stress, this is a little bit of a more philosophical remark now, but I feel that this is actually why I also got interested into this kind of business, is that when I look at this picture, this is just a picture, so you don't have to agree. But when I look at this picture, this is inspired by string theory, of course, you can compute this diagram, and technically we are going to use this insight as a closed string amplitude between some state defining the holographic boundary and some state in the inner boundary, call it the closed string channel. But the advantage of, the advantage of drawing it in this way is that you may also take the open string description. It's the fact that you can compute this in these two ways. The open string description will have a manifest, in quotation marks, microstate counting interpretation. And this is where hopefully the H-modes are going to come from. So I'm just warning you of what is about to happen, but technically we will compute this quantity and remove epsilon going to 0. And there is an issue about boundary conditions, as you may imagine, that I'm going to put here. Yeah.
What is the middle picture representing?
This thing? Oh.
Yeah. Well, I guess I don't understand it.
Yeah, sorry, I have not defined it. I have just borrowed it from yeah. So let's focus for the purpose of this presentation. This has to do with topological quantum field theory interpretation of these things. But in the way in which I'm presenting it here, let's just I may have run out. I'm happy to take this perspective. These are just some extra maps to define some
it's supposed
quantity.
to be like a pair of pants.
Yes, exactly. Yeah. But since I will not have time to get into that, I think I will just keep this picture. But what is important is to remember that we have this call, if you allow me to use this language. Okay. So everything I've said, I could have decided to take a much more pragmatic approach. And in case that some of you find it useful, let me also present that perspective. So given the success that JT gravity has had, we may ask whether there is an analog, the JT Schwarzschild action, but for 3D gravity with no matter, and without any claims about having any UV completion. Can I come up with a toy model for 3D gravity? A la Maloney-Witten, but without having the ambitious program that they had in mind. So I'm just going to take a more effective perspective. If I think about 3D gravity, then, as most of you probably know, I can rewrite the classical theory in terms of a Chern-Simons theory with a non-compact H-group. And what may be an indication that there may be some lessons to learn here is that, especially in the condensed matter literature, there is a claim that they understand entanglement entropy in Chern-Simons theory. There is the famous topological entanglement entropy that appears as the entanglement H term that I alluded to before. And that's the term that they associate with these anionic degrees of freedom that appear when you cut these Wilson degrees of freedom. And they view the anions, or you can view the anions as collective degrees of freedom, described by some topological quantum field theory, and these guys transform under representations of the loop group or representations of a quantum deformation of the group that you have in your Joan Simón theory. The difficulty in our setup, and this is not a minor one, is that these guys are non-compact, and then mathematicians find it hard to define what we mean by traces and all these things. But if we would have this discussion for SU2, let's say, there are very specific calculations. In fact, it's an amazing piece of work. So what I'm going to ask here is whether we can come up with some picture in which there are anions in the gravitational theory when the gauge group is given by this. And I will not have time to talk about for sure, but we may speculate with the existence of some bound topological quantum field theory that explains this thing. Yeah.
Is you wrote Q the deformation parameter?
Yes.
In this case, is it real or imaginary?
It's imaginary.
Or sorry, it's on the unit.
Yeah. Sorry. Yes. Yeah, I will write it generically later. Yeah, but indeed it is. Yeah. Correct. Okay, so just to be fair with the literature, I was confused about this work for a while. There was a very interesting suggestion by Margoud and Berlinde already some years ago, in which they were sharing their idea that 3D gravity negative cosmological constant should be interpreted as some topological phase. And in particular, they were matching what we would call in holography the BTZ entropy of a black hole with the topological entanglement entropy. The main technical input to make this equality precise is that the area term in the gravity side is equal to the log of some Dirac-Solois matrix, dealing with the dual CFT. Now, there are at least two puzzles that you may raise about this interpretation. The first one is that they were relying on the calculation of entanglement entropy in Chern Simons. And in Chern Simons, as soon as you introduce some entangling surface, the theory is definitely not topological, so you get an infinite answer. And then you get the topological case here. Now, this may sound like a very technical remark, but the actual result of this calculation, if you look at the indices, these matrices are not the same matrix. And since you are dealing with an irrational conformal field theory, this matrix is not symmetric. So actually, strictly speaking, the formula doesn't make sense. And then, if you take the actual answer from the entanglement entropy, the black hole entropy is still finite. So we will try to answer this question. I mean, the picture is still correct at the end of the day, as usual, but I'll try to come back to these issues. So the reason I want to stress this is that we have asked some questions which are very general, and at some point we want to ask whether there are differences between gravity and gauge theory, even in the context of 3D gravity. So I'll try to highlight the fact that for this interpretation to hold, I need to tell you why the right matrix element actually will appear in this calculation, but perhaps more importantly, why the entanglement entropy in a black hole setup is finite. And this is something that I want to stress.
On this slide, what is the gauge group? Is it SL2?
Yes.
So A is parametrizing all, is enumerating all little a's, enumerating all
the holonomies of the black hole. Yeah.
Representations of SL2.
Sure. Yeah. That's awesome. So if I call A, P, and P bar, the sum of P plus P bar modulus of normalization is the mass kind of one. Okay. So in case I start having issues with time. Sure. Is there, so let me take advantage of
So these are, so now that we're,
yeah, there are questions about this.
so this S matrix, can you remind me, so diffusion rules of standard, basically Liouville theory, they satisfy also a Verlinde
Yes,
formula?
they satisfy the
standard,
Verlinde.
even though it's not compact,
Yes.
so.
Completely correct, yeah. I'll try to write how they appear more explicitly in a few
Okay, so
slides.
the spectrum of little a I should just think about as the usual Liouville spectrum.
Yes, yes. So in our case, the relevant representations are going to be in the continuous representation of the solid. And these are the ones that we will keep in our toy model, but I need to define that.
Right, but are you having any sort of analog of the boundary states, FCCT boundary states and so on, and these things that appear also in order to make the theory consistent?
Sorry.
So Liouville theory by itself, at least the standard kind of solution to it, there are extra states, not just a continuous set of states, right?
Yeah.
And you take those into account.
Well, our theory is not going to be Liouville, so I'm not going to worry about that. I'm not necessarily saying that I don't need to worry about your question, but I want definitely to stress that the 3D gravity proposal that we will have is not exactly equal to Liouville. But I'll try to define what our proposal is. I mean, it's nothing new, perhaps I should stress this. It's just a matter of interpretation of things that the community has already used when you do calculations in the model.
This needs to be started.
Oh, is the power back? Oh, sorry.
Yeah, well, the light is on there, the green light, the exit light there is on.
You were using the other button, right? And the other command.
Yeah.
Is this working?
No,
It's blinking now.
It's blinking
Oh.
now.
It's blinking
Oh, it's
now.
blinking up. Okay. If it doesn't, I'll try with this one. So let's give it a pause. And I may need you have to unplug, right?
Okay.
I think I can assume that we will not get out of this loop.
Yeah.
It is a crucial moment, I guess. Okay. So the talk is going to have two parts. The first one, hopefully I'll try to go quickly, but of course you should ask as many questions as you want or need to. In order to talk about factorization, as I have tried to stress, I need to give you some Hilbert space in the first place, and we don't know what 3D gravity is in that sense, so I need to give you some model. In a nutshell, what we are going to use is we are going to declare that what is an approximation in a fully UV ADS 332 ADS setup. We are going to identify our theory with the vacuum Virasor blocks in the dual channel. So I'm only keeping the stress tensor. And I'm going to take that partition function not as an approximation but as an equality. That's going to be our proposal. And we are going to study that partition function. Without any claims about this being, in particular, as you guys know, this will not be modular invariant. But we are going to take that partition function and we are going to explore the remaining questions using that setup. I've decided to stress this because otherwise one of my collaborators will kill me, but I'm happy to discuss this off the record, but I think it's interesting to make more precise the connection between our work and Teisner's work, for instance, from a more mathematical setup. I'll mention, if I have time, where Teisner's work appeared, but just to make sure that, the problem that we are discussing, the factorization problem, when you have some gauge field in the bulk, remember you are cutting the Wilson loop but keeping the space-time untouched, if you allow me to use this language. What I'm after is a description of the VTC black hole in which the VTC black hole is itself a Wilson line, and so I'm interested in cutting that Wilson line. In terms of pictures, I'm interested in cutting the Einstein-Rosen bridge. That's what the picture is trying to capture. And more technically, what I'm after is if I can find evidence for the existence of some modes transforming under which group and under which representations. What we will find is that these so-called gravitational H modes transform under a quantum deformation of a semigroup, which is SL2R+. This is the group that Thomas Mertens and collaborators found in a description of JT gravity. People usually describe it slightly differently, so this is a quantum deformation of the answers that they had in JT. So from that perspective, it's very natural to recover their results. Now, what I find that deserves a better understanding, I'm a very simple person, as some of you know, is that using these shrinkable boundary conditions, which I'm going to spell out, this has just been blah blah blah, what we will discover is that this is potentially up to interpretation. But the interpretation of one of the calculations that I will present here is that, especially in a Lorentzian setup, is that our calculation suggests that there is a non-trivial density of states at the event horizon, which is precisely equal to the Plancherel measure of this quantum group. So the non-trivial gauge group that is acting on these entanglement H modes is a quantum deformation of the semigroup SL2R+. That's the Plancherel measure that appears in the representation theory of tension. So, and I suspect that there have to be very good and relatively trivial, perhaps, reasons for why that has to be the case. But coming back to the issue of, okay, Joan, you are going to describe this as Chern-Simons. In Chern-Simons, the calculation gives us infinity. How is it that you are not going to get an infinity? This is something that, at the level of words, what is going to happen here is that these shrinkable boundary conditions that were guaranteeing that the whole goes away and you get the disk partition function is such that it determines the density of states, it determines that this is the group that appears, but as an outcome, there are no descendants appearing in the partition function that controls the contribution of that disk in the limit. And technically, it is the descendants that give rise to the infinity in an entanglement entropy calculation in Chern-Simons. So I don't have anything deeper to say than that, but technically, this is where we will get a finite answer. So at the end of the day, by the way, we are realizing in Madhuf Berlin the picture, but I would say that we are trying to be a little bit more precise. Please, Kevin.
That Q, that deformation parameter, that would be a parameter?
It will depend on the central charge. I will write it down, sorry. Yeah, I should have written it here. Yes, and it's a parameter in the unit cell. Yeah, Okay. Yeah, of course.
In this effective description, you don't allow, it's a Lorentzian description?
I will be mainly working in the Euclidean theory.
Do you allow for topology change? Or
no,
okay.
no.
Okay.
I'm personally quite confused on how to extend these ideas, but I will be happy to. Yeah. So far we are working on the disk. Exactly.
And is it one of the gravitational constraints which gives off the descendants?
In our setup, the absence of descendants will be making sure that the partition function, when you remove the hole, satisfies that the partition function equals the one without hole.
Boundary conditions.
Yeah, boundary conditions, if you want. But that's how it will appear. I'll be quite explicit. Yeah. So let me just remind you of the setup. I'm using the word reminding because I don't want to, I don't claim that there is anything new. We are just going to use some models. So the story goes more or less as follows. I'm going to assume that I start with some parent ADS3 CFT2. You are welcome to take this as a UV complete theory if you want to. Then I am assuming that this is an irrational CFT. I write its partition function. This is modular invariant. I'm reminding you of the notation here. So these are characters. This is the vacuum character. This is the character of some chiral primary H, and the parameters Q, tau. This is all related to previous question, Gabriel's question. So the chemical, the temperature and the chemical potential are beta and mu in my notation, and this is the central charge. So later I will define B in terms of this data, in particular C. Okay, so this is
the Q. This is the Q of the quantum group.
No. This Q is the Q that appears in this.
Very good. Very good.
You are indirectly saying, Joan, you choose a very poor notation. And I agree.
Recognize that
But I
so
could
many
also
letters.
reply saying, well, Q appears here manifestly as
I'm
the
sure.
parameter that
Just
you know
you
better
telling
than
us that
me.
it was going to be in a unit circle, and then you, on the slide after, said e to the 2 pi I tau.
Yes.
I was wondering
Sure.
if that was related.
Yeah. Good. Is anyone confused over what Q is in this slide? Okay, so the claim is that when you take this UV complete theory, there is a universal high temperature regime in which the contribution from your excitations is exponentially suppressed in this limit. And so from the perspective of a full UV theory, the initial partition function is approximated by the vacuum contribution in the dual channel. What I said in words before and what I just now write in equations is we will take as our proposal for an effective 3D quantum gravity theory, one in which the theory is defined, the partition function is defined by chi0. And I'm going to tell you some properties that this theory has. I'm not going to say anything new except for a remark, which as far as I know I haven't seen in the literature. So when I rewrite this partition function, and notice the equality, so now I'm taking this as an independent input from anything else. When I rewrite this in terms of the Virasoro modular S matrices that I had in the parent theory, it allows me to write this data. This is the dual channel in terms of the original cycles before doing the transformation. And this is where these modular matrices appear. Now, in this way of writing this partition function, this has a very natural, again, nothing new, this has a very natural grand canonical partition function interpretation in terms of a sum over P plus and P minus. This is the contribution from the boundary gravitons in the eta function. This is the Hamiltonian, this is the angular momentum, theta and mu are the chemical potentials and the temperature as before. And there is this non-trivial measure which knows about Carly, as you know. When you take large C, these cinches will become exponentials and that will give you, and this is the answer to Finn's question before. And this is the standard writing in terms of a new theory, even though our theory is not good. Okay, so some remarks. This is the answer to Gabriel and Arjun's question. This modular matrix is actually equal to the quantum dimension of the representation P that appears in the sum in the grand canonical partition function. So we are summing over P plus and P minus. If you take a fixed P, if you ask what is the representation of the states that you are counting in that grand canonical partition function, the answer is given by this modular transformation. There is a sense that this is why the H modes in our shrinkable boundary conditions are going to be controlled by this. But this is the reminder that this modular invariance, as you guys know better than me, knows about Calvi. You take a large limit, these cinches get approximated by exponentials, and then you reproduce the Bekenstein-Hawking. But when you play this game, it's not obvious that there is any entanglement interpretation to that statement, and that's what one of the goals of this investigation was to try to see whether I can interpret this thermodynamic statement in terms of entanglement entropy. One way of interpreting this rewriting of this cycle in terms of the dual cycle is in terms of some partition function in which you are summing over a bunch of off-shell black holes.
Could you go back?
Yeah,
so
sure.
I am a bit confused about I think it's just p versus p squared. So the Liouville momentum is p plus and p minus. I know it's not Liouville, but it's Liouville notation.
Yes.
So p plus and p minus
So, yeah.
is those are the Liouville momentum.
I think so, yes.
And then the way you've got squares here is because you're having some kind of on-shell condition. So the space-time mass is L0 plus L0 bar.
Yes,
like
yes,
that.
yes. Yeah. So, okay, sorry for going through this so quickly. So I've written the partition function in terms of the quantum, the momenta that appears in Liouville, as Finn is saying. But I wanted, so here there has been a subtle approximation. I'm summing over all black holes, but there is one that has a dominant contribution, which I'm denoting by P star and P bar star.
Sure, it's just that m minus j you might also reasonably call a space-time momentum, and that is then momentum squared.
Oh, that's
and I understand.
Okay,
That's how it comes about.
But I definitely wanted to go to give a map between the quantum numbers that appear in the grand canonical partition function and the m and j characterizing whatever classical black hole that you started with.
But where did you get that? So this is some kind of string theory construction, right? So how come the space-time mass is related to the conformal weights with that square? I guess I just don't quite understand.
Maybe I'm using slightly different conventions from the ones that you are using, but this map is the standard one.
Yeah.
I'm just rewriting it with the variables that appear in my partition function. The previous one, so those ones.
Yeah. Oh, okay.
And you see, maybe what we have not discussed is the relation between your h and h bar and p plus square and p minus square. So
But also, I mean, it's unusual that the p plus and p minuses are real, so they're usually complex. This was Liouville, right?
Yeah.
It's not. Right?
yeah, but this is the map between your Canonical primaries and your so this is the square. Okay, let me do this. I've said that this eta is, so for fixed people are p minus, this eta is the partition function account for the boundary gravitons, but all this is known. One technical thing, and please correct me because there are experts here that know much more about GT than myself, is that if I take, so let me remind you of a very, for someone like me, this is a very interesting piece of work by Ghosh, Maxfield, and Turiachi. They were pointing out that the partition function of JT appears universally as a near extremal limit of a 2D rational CFT, which is the set that we have here. Now, what we have done in our proposal is we took a large temperature approximation of an ADS CFT UV theory. We've taken the vacuum Virasoro characters as the full theory. And now, in that partition function, I could ask what is the behavior of that partition function independently of the parent UV at low temperature. You could ask me, if this is a good toy model, how can I reproduce JT out of our story? So, if I take this limit, what we get, without necessarily being near extremal, which is controlled by sending this I nu to 1 in my notation. Remember that in JT you get a single copy, because one of the sectors decouples. That's what the near extremality does for you. In this setup, in this double scaling limit, you can see that what you get is the square of the JT partition function, where the argument in both of the partition functions does not involve the extremal parameter. So I actually think that this is interesting on its own right, but I'm just mentioning this as a technical remark. So this means that in terms of doing calculations, this would allow you to go beyond certain calculations existing in the notation. I'm going to skip the relation to Kohler and Jensen. And here I'm just summarizing what I have said before. As usual, I repeat myself a lot. So because of my approximation, this is not a model by invariant theory, so you may worry about this, but this is my choice of toy model. Global ADS3 is not part of my Hilbert space. Again, since this includes JT, remember that in JT this is also true. There is a distinction between extremal Poincare and the vacuum. And for those of you that have thought more in terms of boundary conditions and the Kohler and Jensen description or Renault's description of this system using also Chern Simon variables, what has happened here is that we have done some swap between the space cycle and the time cycle, and our boundary conditions are such that we are imposing trivial monodromy around the Euclidean time, but we are allowing arbitrary monodromy in the space direction, and this is what allows us to have a sum over defects, which is the sum over people and people. But you know, the analysis of Kohler and Jensen basically goes through just swapping cycles. What they call space, we call time, and so there are. Okay, so now I've given you a Hilbert space, and now I would like to use it in order to discuss bulk factorization. Sorry, Joan?
Yes, I know you said you were going to skip Kohler and Jensen, but could you say just one more thing about the relationship between what you did and what they did?
So what they did is that they identified the Alexeyev-Shatasvili geometrical action as the action controlling the fluctuations around a given background. And their degree of freedom is describing some reparametrization of the cycle, satisfying this boundary condition. The important thing is that this boundary condition, which has winding 1, is in the space direction. What we are doing here is swapping the time and the phi direction. So technically speaking, this is the condition that I'm imposing.
And why is that a good thing to do?
Well, it's a good thing to do because it allows me to sum over arbitrary insertions of defects in the spatial direction. Whereas my interpretation of the Kohler and Jensen calculation is that you are studying fluctuations around a given value. And I'm not saying this in any negative way. I'm just highlighting that the switch in the boundary condition is allowing me to interpret the problem differently.
I see.
See the outcome of the description. But our claim is that if you use this formalism, you would still get the same effective action in terms of this diffeomorphism, but the boundary conditions in the time direction. Everything complete. Thanks for asking. Okay, so when I was answering Subrat, I already mentioned this, but let me just back off and go back. So our discussion right now has been more in getting some data from some parent UVCFT, but now I'm going to take the two-sided, I'm going to try to describe the two-sided bulk Hilbert space and relate the objects that will appear here with the ones that we could borrow from our toy model. So if I go to the bulk, remember that because of the Brown-Renault asymptotic ADS3 boundary conditions, the Kac-Moody algebra that you have in the WZW formulation of the Joan Simons gets projected into a Virasoro symmetry. Now, what we have in the Joan Simons formulation of 3D gravity is the description of two chiral sectors per boundary, and the degrees of freedom, the boundary gravitons, are these arbitrary functions L and the analog L bar, which are functions of tau and phi. Since we have two boundaries, we will have two copies of these structures, altogether 4 stress tensor components. And because of what we discussed before, the zero modes of these stress tensors are constrained to be the same. So that's what prevents the factorization of the Hilbert space from the bulk. That's the argument that we were saying before, that such constraint on the conserved charges is true in a number of dimensions. Now, modulo this constraint on the zero modes, this constraint, can describe the bulk Hilbert space as a tensor product of excitations in the left and the right, as a direct sum of excitations in the left and in the right, summing over all possible representations P, which are the labels that were appearing in our grand canonical partition function, that's the same P. And so the one example is, let's take this for a fixed P. The states in that setup are labeled by P, by the zero mode that remembers that you have cut off, that you have done a little circle of reaction, and then you have the descendants. And you have a similar parametrization of these vectors for the other totals and for the other tidal sector, which would be P bar or P minus. But remember that there is the zero mode constraint. Now, let me go back to the thing that I would like to make sure that goes through. So now we would like to revisit that question about how we can come up with, what Onkar said, with a canonical construction. Now, the idea that we are following here is that coming from the bulk, I have this picture in which I introduce some cutoff surface E. But this would be the picture in JT, which I will revisit in a second. But in our 3D story, we have an extra S1 cycle. So the idea of imposing these shrinkable boundary conditions is going to be that you have a solid torus, and you want to remove this blue interior torus, which is removing this cutoff along the entire cycle. And this shrinkable boundary condition says that when you take the size of this inner cycle to 0, you would like to reproduce the holographic boundary partition function with no hole. That's technically what we will try to do. So, since this may appear, before this, so to stress the potential microstate in quotation marks, remember there is nothing you really complete here. If I start with the original Euclidean solid torus, what we want to impose is that we remove a very thin inner torus, take the limit of epsilon going to 0, but from the open string perspective, I can interpret this calculation as a reduced density matrix on one of the sides of this construction. So perhaps this is more explicit here. From the bulk, I start with my Euclidean partition function. This is how the bagel on this Cauchy slice, this is how it looks like when you construct the Hartle-Hawking state. And the factorization map, what it will do if we manage to write it down, is to include this cutoff surface, splitting the bulk into some subregion B and some subregion B bar. From this perspective, this calculation can be interpreted as the trace of the reduced density matrix on rho B, if you succeed in defining this factorization map.
Sorry, can I ask, it's a few steps back, but I just got this back. So you said that the boundary condition between L and R was that they were matched in such a way that the L zeros agreed with one another?
Yes, sorry.
What
Yes.
happened to the L plus minus 1? Or do you have any condition between those, or they come free to be whatever they want? Or do you also, do they have to agree between L and R as well?
The only quantum numbers that need to agree are the zero modes.
Yes.
Yeah.
There are 3 zero modes, not just L0. And I'm saying there's also an L plus and an
Yeah,
L
so
minus.
so the answer is yes. That's
Those
what
also
gives you
agree.
the mass and the angular momentum constraints. Yes. And this is related to what Arjen was saying, that in JT the SO2 charges need to be matched.
Yeah, I just didn't see plus minus 1s there.
So to fix things, here in this bagel, you have the description of the Hilbert space in terms of this holographic boundary, which is labeled by L. The interior cycle of the solid torus in this bagel is the other holographic dictionary. And what we are introducing is this extra entangling surface. And if you Lorentz continue, that's how the picture will look like once you have introduced this cutoff surface, the entangling surface. We have not defined the map yet. So in JT, where it's easier to write these things down in terms of pictures, for instance, so let's try to spell out this reasonable boundary condition in JT gravity, for instance. So in that case, one of the sides of our condition would be, let's compute the partition function on the disk. And this partition function should equal the anomalous partition function when the size of this hole goes to 0. Now, one trick that you can do technically is that when the size of this entangling surface, let's call it epsilon, is finite, this is anomalous. That's what I was trying to say before. You can view this calculation as a closed string channel amplitude between a holographic boundary, which is the red one, and the inner boundary, which is the blue one, of size epsilon. If I introduce a resolution of the identity in terms of all the set of different insertions that I can include, I can compute this anomalous partition function that depends on the two sizes, the holographic size and the entangling size, as an integral over the quantum numbers of all the insertions that I can include, times two partition functions. In some sense, I'm playing Wheelen's game of doing partition functions. I'm labeling this in terms of quantum numbers. And I have a contribution from this left picture, which I will denote inner partition function. It depends on what I have included and the size of the entangling surface. And an outer one, which will satisfy holographic boundary conditions, which depends on the physical beta and the same insertion here. All these quantities are known, and you can just make sure that that condition is satisfied. What I'm going to do now is write that condition in 3D. But I hope that is the logic clear. So I think that I have it here. Yeah. So the anomalous becomes an anomalous times a cycle. There is still one picture of the calculation in which it looks like an amplitude between some inner entangling surface and the outer in red, the outer cycle of, the shell of the solid torus, tau 2. I will be interested in taking the size of tau 1 to 0, but I will use the same trick of introducing a resolution of the identity in certain Wilson loops. But the mathematical problem is that I have a partition function with no holes, characterized by holographic boundary conditions tau 2. And this can be written as a sum over Wilson loops of some inner partition function where the size of what I am excluding here goes to 0, times the outer contribution. And the claim is that we would like to identify what is the structure that appears in this, what I have called E. What is the boundary condition that I'm imposing there, as Finn was alluding to, in order to make this compatible. And what I want to, let me check time. All right. So the calculation is split into two pieces. Let's discuss the one that only involves holographic boundary conditions. So, borrowing from the literature, the outer partition function for some fixed lambda insertion is given by some beta Soro character in the dual channel, and this is the answer that you get. Now, the inner, this is where things may start deviating, so it's important to stress this point. When I could have written the same equation for Chern Simons, and I may have been tempted to say, well, the answer to this problem here is given by some inner partition function, which is given by some Moody character, which is given by this character in the dual channel. And what I want to stress here is that in the Chern Simons answer, which is given by this expression, this character contribution depends on the eta function that has descended to the power cube. So let's forget about the cube, but what is important is that you have a contribution from boundary gravitons, if you allow me to use that language. And so when I take the limit of tau 1 going to 0, this partition function will diverge. So in the Chern-Simons answer, which just uses this as input, the partition function diverges, and the shrinkable boundary conditions that we wanted to impose to make sure that the hole is closing smoothly is not satisfied. If I ask the question, is there a way of fixing this using some Laplace transform, for instance, for the inner partition function, the answer is, remember, I'm trying to solve this equation. This is fixed by holographic boundary condition, the coset construction. This is fixed by the solid torus partition function. This is not known at this point, but we know what is the cost of introducing this Wilson loop. The answer that we got is given by this expression. This just follows from imposing this shrinkable boundary condition. If you don't like that condition, you should impose some other one. So that's the input in the calculation. Now, some remarks. This product of sinches, perhaps up to a factor of 2, they are the Plancherel measures that were appearing in the very initial step of the Virasoro modular matrices. So that's the same statement as before, but the origin of it is coming through that. And remember that we are taking a limit in which the size of the inner cycle is going to 0. We want to interpret. This is a little bit of a more Lorentzian interpretation, so not everyone may agree with this. But my interpretation of this fact is that there is a non-trivial density of states for each value of P that is localized in the entangling surface. And this beta 1 contribution here is just shifted in the limit that you approach the Lorentzian.
I may be completely losing. I must have completely missed your major point. So you were just explaining that the affine SL2 is no good. That's what I maybe would have thought. You're absolutely right. That's what I would have thought. And you're saying, the correct one is the quantum group. How did that happen? Where did that come in? Where did you put it in? I thought you all along said I'm going to do SL2 Chern-Simon theory, which is affine SL2. So what I missed the slide.
No. I may have not explained myself. I'm sorry. I am imposing this condition. If instead of talking so much, I would have just focused on this, I would have said, I want my partition function in the absence of any holes. This is fixed.
And you're saying an SL2
and
affine SL2R just doesn't
there is an eta here. So this partition function has descendants. But these descendants live in the holographic boundary, so you should have those descendants.
Well, you're saying that here I might have proposed affine SL2, and you're saying just no good.
Yes. So the short summary is that if I take this equation, which is a constraint that you may not want to impose, but if you impose it, and if you also use your intuition that this inner partition function should be computed using characters of the Carmody, because the interior inner surface doesn't satisfy Brown and no boundary condition, so there is no reason for you to use the Virasoro characters. If you use the Carmody characters that reproduce the Chern-Simons entanglement entropy calculations in the condensed matter literature, this equality is not satisfied. And moreover,
this boundary condition, of course, it seems geometrically incredibly reasonable, but just for perspective, in people doing, for example, higher spin Chern-Simons theory, then they found some kind of boundary condition that was the right one, which was not entirely trivial. It was something like some part of the center of the spin group or something like that. So anyway, so that was some kind of result that was then accepted as being the right boundary condition. But that was SL2 or affine SL2?
I'm not aware of this higher spin story, so I cannot compare.
That was just going to SLN instead of
SL2. No, I understand.
And then, check n equal 2 and ask what the answer is, and it's,
okay.
I think, well, I don't know if it's different. It's a boundary condition.
It's a boundary condition.
Yeah. Okay.
We have imposed this one. You may not agree, but this is the one that I have imposed.
I am completely agnostic. I trust you.
No. You shouldn't trust me. I'm just telling you what we did. this was an assumption, right, in this analysis. I have not derived this from anywhere. It may appear reasonable, but I'm just highlighting, and physically I think that this is
It's
important.
reasonable, but gives something that was perhaps not what you expected.
Maybe.
So you might go back and say, am I sure it was reasonable? Okay, fair enough.
Well, it will give you a finite entropy, so that's something potentially good, because this theory is fully quantum, not in the sense of a UV complete theory, but in the sense of, I will not have an area term divided by epsilon, precisely because this boundary condition fills that possibility. Now, if you ask me, is this possibility unique? I have no answers, and it's a fair comment that you make that what is the comparison between this and the other thing. Okay, so what, the most important thing that I wanted to highlight is that I would like to interpret this as the presence of some density of anions in that entangling surface, and the fact that this gives me on the face, not unsurprisingly I would say, the information about this Planck relation. I'm also learning that that this A and A bar will transform under representations of this quantum symmetry. Okay, so I think that I have stressed this thanks to your questions. So the key point, this is a little bit of a physics recapitulation. This is perhaps a technical remark, but in case that it helps to some of you. One other way of phrasing, well, we believe that another way of phrasing this difference between the Chern-Simons gauge theory calculation and the gravity calculation is that imposing these drinkable boundary conditions, when you rephrase it in terms of which bulk geometries you are summing over, it prevents the contribution from conical defects in the Euclidean time direction, whereas in Chern-Simons those configurations are sum over. We make this a little bit more explicit in the paper. And as I said, at the end of the day, I think that we are giving a stronger evidence of the huge insights that were already made in the McGutter-Linde paper. Now, with the remaining minutes, I will try to make some comments on the factorization problem, or the factorization map. So in this picture, what I have in the lower diagram is the top of the bagel, where I have defined some H bulk based on our toy model, and this is where I have these boundaries, and in these boundaries I have the Virasoro H modes. These are the standard boundary gravity, I'm sorry. And then in the interior I have defined this through this map. I define this cutoff entangling surface where we have identified the existence of this SL2R plus Q H modes. The question that we want to answer technically is whether we can write some Hartle-Hawking state which is compatible with the partition functions that we have discussed here, which still has about trace interpretation in terms of the open string picture, and which involves quantum numbers that transform under this quantum group. There are two copies because we have two chiral sectors. And the answer for the Hartle-Hawking, as many of you may have guessed, is that due to the structure of the bagel in our toy model, there is a split between between the two chiral sectors. So we should write down some tensor product between one chiral copy and the other chiral copy. And the one that satisfies to have the right inner boundary condition, inner product, is given in this expression here, where this knows about the measure, and the notation for this curve here is introduced here. So I'm trying to reduce the notation, but I hope that this will not introduce confusion. So remember that I have that I need to project the calc movie through Drimfeld-Sokolov, I need to satisfy things constraints or on the SO2, and on top of that I have descendants in both chiral sectors, and this is a tensor product summing over all possible descendants. Now, what we do, and this is a part that I'm not terribly satisfied, but what we do by hand is, I'm going to define, this is an answer at this point, I'm going to define what you may call some subregion, some subregion state. I'm trying to factorize this into S and S bar. Now I know that this S is transformed under this quantum semigroup. And I'm going to define them in such a way that they keep track of the zero mode where I'm working, which is P. They will be independent of the descendants because these quantum numbers the representations of these guys don't have descendants because we know the density of the states don't have any descendant contributions. And our natural guess, I'll try to connect this with the structure of a quantum group, but perhaps this is the wrong order to present things, is that I'm going to define my factorization map in terms of this case that I have introduced before, in terms of a sum over all possible objects S that I can add in here, belonging to the different subregions, with the condition that when I trace over one of them, I get the right measure. I should say, for those of you that may have thought about this or that are worried about this, is that because of the non-compactness of the gauge group, defining these traces, for instance in JT, it requires some regularization. So there may be something non-trivial in this definition. But at least in the JT case, we do know of some regularization with this property is satisfied. So we are defining our subregion states in this way.
Joan, may I ask a question?
Yes.
So there is no, maybe it's there in your picture on the right, there is no S-dependent non-trivial measure in this integral? So you're just integrating over S, there's no additional S-dependent measure?
Yes, I think you're right.
But there's none?
Yes.
There is or there is none?
There is no,
No,
sorry,
yeah,
yes,
yeah.
there is, yeah. And
I see.
morally, this is a little bit also why I was asking you whether in your story, the dependence on those polar contributions, I was interested in the dependence on that measure, but I'm not saying that there is a relation, but yeah, it would be interesting if some of these ideas can be applied in higher dimensions. So this quantum semigroup has appeared. I have not even defined it, and I'm not an expert. But you may have seen the first definition somewhere. So here, this is one possible definition. A more algebraic based one is in terms of some matrix in which the elements of the matrix are operators themselves, satisfying these non-trivial deformations of the standard commutation relations. Now, the one that I will be using, and this actually motivates our factorization map, is that anytime that you have, okay, let me not rush. You can define, in our case, a semigroup, a quantum group, G, as the algebra of functions defined in that group. In particular, if this would have not been, if we would have started with no quantum deformation, when you turn on the deformation, this definition allows you to study the deformation at the level of the algebra of functions. That's why the reason why this definition is more powerful than others. But what I want to highlight, this is just, just mathematics are very deep, but is that you have a natural basis for this algebra of functions. It's typically non-commutative because of this operator nature of these entries. And the elements in this algebra are the products of these matrix elements of your group. Okay? That's the intuition. But whenever you have these quantum groups have the structure of a Hopf algebra. And whenever you have a Hopf algebra, mathematicians tell you that you have two kinds of products. The one that we intuitively have in our minds, which is given two functions, f1 and f2 on G, I just multiply them and give me something else. But there is a coproduct in which, given an element in my basis, Gij, the quantum group in a very natural way it splits it into two. From a physical perspective, that looks like a factorization. It's a mathematical structure that looks like the kind of factorization. In fact, the factorization into the Yang-Mills is inspired by this, as I will stress in the next slide.
So in this second definition, you did not include the definition of Q. So that is
no,
the product
because
or the co-product? Well,
no.
okay,
Sorry, Finn.
Okay.
This is very general. This is for energy,
Okay.
and I will apply this to SO2
okay.
Q plus 2R.
Okay.
But this is true for energy. I'm just trying to stress that something that I learned in quantation bar, I'm still infinitely ignorant in this topic, of course, is that whenever you have one way of defining quantum groups is in terms of Hopf algebra structures. And for any group, G, these Hopf algebras, besides what we would have called the standard product, they have another object which they call coproduct, which mathematically is given in this way, but in today's talk, this looks like a structure that you could use to factorize Hilbert spaces. So, as Finn was alluding to, we are going to apply this coproduct, the existence of this coproduct, to SO2QR plus.
Of course, I mean, in this case, there's nothing quantum with this coproduct. That was just
Sorry.
So the quantumness is in the product in the way you were defining.
Sorry, I agree. Yeah, the terminology of quantum groups in this context is a little bit misleading for physics audience. But yeah, I feel that what they mean by quantum is that whenever you have a parameter Q, you are deforming.
Yeah. No, what I mean is that if you take the normal SL, it's still a algebra.
Yeah. Sorry, I agree. Yes, absolutely.
The deformation happens in the product.
Exactly. Yes. Okay, so if we want to apply, Bijou will kill me, I still have 9 minutes. So we want to, coming back to Finn's remark, this is for any group G. So we would like to apply this to SLQ plus 2R. Now, this is just a little bit of a reminder of a result for standard groups, which is that whenever you have any square integrable function f of g, it is mapped to another representation through this left and right action. So it furnishes another representation of g times g. This is one way of motivating, if you want to, the important theorem in mathematics, in representation theory of the Peter-Weyl theorem, saying that representation decomposes uniquely in terms of an irreducible sum of representations Br and Br star. What this is doing for us is that given some group G, again, this is still general thing, sorry, I have some complete basis, I give you some group element, I give you some representation of the matrix elements A and B, and this gives me a complete description of that space. Now, something that I'm going to use implicitly in the coming slide is that mathematicians tell me that one way of reinterpreting this story, and which has been extended in a much more abstract way that I cannot present here, is that I can think of this data as a way of reconstructing the group itself. So if I give you what they say, the full set of representations of a group G, I can reconstruct the group G itself. But I think that I'm stressing this too much. Now, so if I look at the math literature, of course, we didn't show this, I would not be able to prove this, and now I'm trying to bridge with the result that some of you may know of Consota and Teichner. What you learn from the work of Consota and Teichner is that the L2 of the quantum semigroup that we have uncovered into today's shrinkable boundary conditions satisfies this Peter-Weil generalized theorem. I'm using generalized because here everything is continuous. There is this non-trivial measure, which is the Plancherel measure that we have reproduced physically by these shrinkable boundary conditions, and this is the same Q that you guys were asking about. There are explicit representations of these representation matrices for this group computed in an amazing paper by Ip. Now, the claim is by Consot and Deschner. My understanding of how they got this answer is that they actually solve, and maybe this is going back to Phil's remark, I don't know, they solve the modular bootstrap for a Liouville theory. And what they found is this answer. Now, the way in which I would like to interpret the result is that there is a one-to-one correspondence between representations of our semigroup, quantum semigroup, and representations of the Virasoro algebra, because they solve the bootstrap of a Liouville theory, and I want to interpret the Liouville theory as a universal and rational 2D CFT. From that perspective, what I'm learning is that the matrix elements of a group element G belonging to the semigroup that we have uncovered in these shrinkable boundary conditions should provide a complete representation for the states in our problem. That's the main technical output of this discussion. In terms of trying to give you a little bit of an intuition, I gave you an answer perhaps too early on, but now we could revisit, is it natural to define that answers given the fact that we have a Hopf algebra structure here? So now that we have seen that we have a quantum group, when I split this in a codimension to surface, I could use it is natural to use the coproduct structure that I have in that Hopf algebra to define the factorization map at the level of the representation matrices that label my states. So if I give you some element G and some element of the basis of L2G are AB, it's natural to use the coproduct in order to split it in this way. And even though this looks like a product of matrices, it's what I want to stress here, and sorry if this sounds silly to you guys, is that in the context of the discussion that we are having, the index C is counting H modes. You have factorized a single element into a product of two, and you are summing over all the objects that can appear in the interior. So if you think in terms of these group elements as path-order exponentials of connections, these are the non-local degrees of freedom in physics. When I do this coproduct factorization, if you allow me to use this physics jargon, I am identifying two objects with G1 and G2, and I am gluing them. But I need to tell you what are the objects that can appear in between. When I have matrices, these are indices, and I just need to tell you in which representation they are. But when I don't know, and I can count the dimensionality of the representation, and the log of that representation is going to be the entanglement entropy. You don't have to buy this, but I'm trying to provide some pictures in 2D Young-Mills and other simple quotation marks theories. This is what's happening. So going back to the remark by Finn, I would like to say, well, there is this mathematical structure. Physically, I have tried to stress the important thing for me is this shrinkable boundary condition. That property at the level of the partition function allows me to identify the existence of some non-trivial density of states at the entangling surface. But now there is this complete mathematical structure for any G, or we have a monkey interested or non-interested. At least. The good thing is that if you don't remember anything about this talk, I hope that you remember about it. Okay, that these mathematical structures, perhaps too abstract, apologies, but I wanted to share it in case that it illuminates some of you. This is something that I learned in present maths. So applying this structure to the actual outcome of these shrinkable boundary conditions, what I'm learning is that this space, this algebra of functions living in that entangling surface, these are labeling the S's that Gabriel was talking about. And so almost by construction, if I define the factorization map in terms of that product, that guarantees that what a physicist would call entanglement entropy, it equals the log of the dimension of those entanglement modes. And this is precisely the Plancherel measure. And when you take the large limit of this, you reproduce the Genstein-Hopper. So,
So what is the physical interpretation of Q? What is this Q related to?
I don't have a good answer for that, Diane. You mean a physical interpretation for Q? I wish I could answer that. I don't know.
The answer doesn't depend on Q. Okay. The answer will not depend on Q at the end of the day. Is it? The final answer for the entropy.
Yeah, that's right.
It will not depend on Q.
Yes, I think you're right. Yes, you're right. But I don't know. Yeah, I don't know if someone has a comment. I don't have any physical. Well, okay. So sorry. This may sound like a bad way of answering your question, but this, in case it helps, this quantum group structure, I don't know if this has appeared in, I think that in some talk this appeared, but in a much more complicated framework, of course. This quantum deformation is trying to take into account the braiding properties of when you fuse different Wilson lines around different cycles, there is a non-trivial structure. So one way of mathematically encoding those properties associated with braiding and the Q that appears there is to capture that perspective. I don't know if that helps, but I don't have a sharp answer for my understanding of your question.
So your little b is effectively the central charge, right?
Yes, yes.
So it's very, very large, or is it very small? Because you made a duality at some point, so
in our construction, once you take...
Is b near zero or near infinity?
So in our construction, C is finite. Once I give you, forget about the UV theory, if I would have given you that Z is equal to the vacuum character in the dual channel, and that's my definition of some effective quantum theory, I'm working with finite C. It's true that in some slides I was taking large C, but when I write this answer, it's for finite Q.
Finite but very large.
Not necessarily. When I write this equation, no. But if I want to reproduce
I pi b squared, and what I'm after is that something that has many faces? Because it sits in the circle, but has it somehow gone many times around the circle?
When
or
I
is
take
it the identity?
When I take large C, yes.
So it's a complicated braiding structure or something. Because it got very complicated faces.
I wish I would have something to say, but I don't know. Please.
Optical products basically used to create some kind of multi-particle states.
You could, the way in which, sorry, yes. I'm a little bit biased in the discussion because this is where I was coming from to, some of these structures I've learned myself. I was very ignorant about these things. But the way in which I was thinking about this coproduct structure is the fact if I give you a single Wilson line and you want to break it into two, I'm using the more abstract notion of coproduct, which for mathematicians is a very natural way, a very natural thing for of algebras, as Costa stressed. I'm thinking that I am literally, this is allowing to have a mathematical formulation of the breaking of the Wilson line into two pieces in a gauge-invariant way. I don't know if this answers the question. I'm just trying to give some motivation, some intuition.
Sure. Time.
Yeah, time. Yeah. So okay. So in this I'm closing. I'm closing. Just to stress, in our construction, We are not claiming anything beyond that. I wish we could. Black hole entropy in this effective 3D theory equals bulk entanglement entropy. We have proposed some factorization for the Hassel-Hawking involving these drinkable boundary conditions. And perhaps from a physics perspective, what I would like to highlight is that the boundary gravitons at both boundaries are spectators in this factorization map. But when I look at the entangling surface, this satisfying these drinkable boundary conditions, which we have agreed you may like or not, this was an input, so it would be nice to derive this from principles of topology. I'm told by mathematicians that drinkable boundary condition should be guaranteed by the axioms of Atiyah, but I don't understand these things, so I cannot report. But from a physics perspective, I think that this is an important comment, which is that these drinkable boundary conditions in 3D will no matter, so the excitement is limited, has no descendants, so that gives rise to a finite answer. And I will stop here. Thanks.
Since we're way over time, let's just save questions for lunch.